We have already learned the techniques on image segmentation, and basically the output of the segmentation algorithms will give us the entire image being partitioned into several regions. Now the question is that how do we consider these regions, or in order to do further processing with the computer, okay, how do we represent the various regions? And another aspect is how do we describe all the different segmented regions. This is of utmost importance in the field of digital image processing. So this is what we are going to study today, that after the segmentation algorithm, after application of the segmentation algorithm, when we got the various regions, how to represent that. Okay, this is what we are going to discuss today. And basically the representation of the regions we can classify into two major areas, that's to say the representation techniques. So representation of regions, this can be done either using the external characteristics of the region and the other is the internal characteristics. Now what do we mean by the external characteristics of a region? Obviously, when we say external characteristic of a region, we mean the characteristics of its boundary. Alright? So basically external characteristics always refers to the boundary of the region, and internal characteristics obviously refers to the pixels which are composing the region. Okay. Now both these representations are well popular in the field of image processing, and in this class we will be discussing about the external characteristics mostly. The external characteristics, or rather the boundary characteristics of a region, okay, is there the main focus is on the shape of the region, okay, whereas when we consider the internal characteristics, there our focus is on the color or the texture of the particular region. Alright. Now in case of boundary based representation, okay, the features which we normally choose are the length of the boundary, the orientation of the straight line joining the extreme points of the boundary, or the number of concavities present in the boundary. These are just some of the features which are used for the boundary representation of any particular region. Alright. Now another requirement is that whichever feature, okay, we choose for the representation of a region, okay, ideally that should be invariant to translation, rotation and scaling. Why? Because when we describe a particular region, okay, its description should not depend upon at what orientation we place that particular object. Alright? Supposing this is the object, okay, whose boundary we would like to represent. Now obviously this object's characteristics, okay, should not change if we place the object somewhere over here, okay, with some translation and with some rotation we place the object in a different position, but even then its characteristics should not change. Or supposing when we take the image of this particular object, at one position we are getting an image like this, and next time when we capture the image we may just alter the focal length of the lens, or rather we may take it under a different scaling condition, okay, whereby the object may look, overall object may look slightly bigger or slightly smaller than this one, okay. Even in that case also our shape characteristics, or rather the region characteristics, should not change. Okay, so we must look for such kind of descriptors which are invariant to translation, rotation and scaling. Alright, so we will be considering the external characteristics for representing a region, okay, today. Now in this we will be considering the various kind of representation schemes, okay. And the first one which we choose is the method based on chain codes. Now in chain code what we do is that we choose 4 different directions. Actually 4 directional chain codes are possible, or 8 directional chain codes are also possible. So first we consider the 4 directional chain code. In 4 directional chain code what we do is that we consider 4 different directions like this. Okay, that means to say when we traverse a particular boundary of an object, okay, we will be seeing that in which direction do we travel. Alright, because when we travel along a closed contour, okay, when we travel along a contour, at that time we will be changing the direction. Sometimes we may be traveling to the top, sometimes we may be traveling to the left, sometimes we may be traveling to the right, sometimes we may be traveling down, okay, in any one of these 4 directions. If we consider a 4 directional chain code, okay. Now whenever we are traversing, okay, and traversing along a contour, at that time the direction of travel is being indicated by a particular number. So these 4 directions which we show over here, they are indicated by a particular number. So in the 4 directional chain code representation we consider this direction, that is to say the right hand side direction, as the direction number 0. Alright, the top one we take as direction number 1, the left we take as direction number 2, and the right we take as direction number 3. Now this means to say when we have a boundary like this, say supposing our boundary is consisting of a set of pixels like this. Okay, so we have considered each one of the grid intersections over here as one of the boundary points, and let us choose any starting point. Supposing this is our starting point, and from this starting point we will travel along the contour of this region. This is a particular region which we have chosen, okay, and the points which are marked with red, they are nothing but the boundary pixels of the region. So this being the starting point, alright, we will be traveling along the contour, and let us say that we are traveling in the clockwise direction. Let us specify that we are moving clockwise. So if we do that, then when we start from this point, in which pixel we will travel?
0.
Yes, so we will travel from this pixel to this pixel, and the direction is 0. Let me write down the chain of the direction changes. So this is 0, and then from here to here, what is the direction? 1. Again here 1, then here 0, 0, 0. Now we are traveling down. Alright, so it is 3, again 3, again 3, again 3, and now we are traveling to the left. So 2, 2, 2, 2, then up, that means to say 1. I am just continuing beyond this point, 1, and then 1. Okay, and we have traversed the contour completely. Okay, so this contour of this region, let us call this as the region R. Okay, and the contour or the boundary of this region R can now be described by a chain of codes like this: 0, 1, 1, 0, 0, 0, 3, 3, 3, 3, 2, 2, 2, 2, 1, 1. This describes a chain of codes, okay, which completely describes the boundary. Obviously, is this a unique representation of this boundary? I mean, do you think that it is a unique representation? No. There are two things. Firstly, that it is heavily dependent upon the starting point. Okay, if we hadn't considered this as the starting point, supposing if we had considered this pixel as the starting point, okay, then the entire code would have been different, or rather shifted, obviously. Well, supposing if we tilt this entire object by 90 degree, let us say, okay, that means to say, let us consider the object now like this. This is the same object, okay, but what I have done is I have just tilted it by 90 degree. Do you think that the code remains the same? Obviously not, because our directions are also changing. These direction numbers are changing. Alright? So, naturally we have to evolve some system whereby we can make it invariant to rotation. Effectively, if we give a rotation to this object, okay, the chain code should be invariant, okay, or it should even be invariant to the starting position. Okay, so we should look for such invariant features. Nevertheless, let us describe yet another type of chain code where instead of taking the 4 directions, we will be taking the 8 directions. Alright, now the 8 directional chain code is defined like this. There we take the 8 directions. This is one direction, 0 degree, we call this as 0. This is the 45 degree direction, which we call as direction number 1. This is the 90 degree direction, which we call as direction number 2. This is 135 degree, which we call as 3. This is 180 degree, which we call as 4. This is 225 degree, which we call as 5. 270 is direction number 6, and 315 degree is direction number 7. So this forms the 8 directional chain code. And obviously the method of forming the chain code is same as before. Supposing we have a contour of this nature, alright, and supposing our starting point is over here, okay, then what should be the chain code from here to here when we are traveling in the clockwise direction? 1, 2, 2, this is direction number 3, 1, 0, 0, 0, there are 3 zeros. Then this is direction number 7. Then 1, 2, 3, we have direction 6 continuing. Then we are traveling in 5, yet another 5. Then we travel 4, 4. So we continue over here 4, 4, and lastly we have direction 3. Alright. So here there could be 8 possible elements, okay, and our boundary neighbors could be the 8 neighbor pixels, okay, whereas in the earlier case our boundary neighbors could have been only 4 neighbor pixels. Alright. Now even this 8 directional chain code also, we find that it is dependent upon the starting point, and it is also dependent upon the rotation. Okay, if we rotate this entire object, okay, the direction codes are going to change. So obviously we should try to make them invariant. So first thing is that how to make it invariant to rotation, or rather how to make it invariant to starting point. That is what we are going to study now. Now depending upon the starting point, as you have already said, okay, our code could just circulate. That means to say that if instead of this we take the starting point as this one, then it would have been simply 2 would have been the starting point, and 2, 2, 3, 1, 1, 0, 0, 0, 0 like this up to 3, and then the last code would have been 1. Simply a circular shift. Alright. Now the method that one applies is that you keep on giving circular shifts and choose the starting point such that you get the sequence which we get, the sequence of chain code which you get, okay, that forms the minimum integer. Okay, obviously this is of course this is too big a number, but here this entire thing you can imagine as a single integer consisting of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 digits. You can imagine that this is a 17 digit integer. Okay, obviously if I make the starting point as 2, the integer count is increasing. This is starting with 2, 2 something something. Okay, now obviously this cannot be the starting point, even this cannot be, but let us come to this point. If we choose this pixel as the starting point, then code is 0, 0, 0, then 7, 6, 6, etc., etc. Okay, and apparently this is the minimum integer, okay, that can be described. Okay, had we chosen this, okay, this is also 0, but it would have been 0, 0, 7, not 0, 0, 0, 7. So obviously 0, 0, 0, 7 onwards becomes a minimum integer, and not the 0, 0, 7 or 0, 7 starting integers. Okay, so the minimum integer which we get is 0, 0, 0, 7, 6, 6, 6, 5, 5, 4, 4, 3, 1, 2, 2, 3, 1. Okay, this is the minimum integer we get. And what is the starting point then? Obviously the starting point which gives this minimum integer sequence is this one. Is it this one?
Yes.
Okay, so this pixel gives us this. So the idea is that whenever we have, if we have to match this particular region with another reference region, we never know that in reference region which one we have chosen as the starting point. Okay, but if you uniformly adopt this approach that always choose the starting point as the one which gives you the minimum integer chain code sequence, okay, then you can match one region with another based on its chain code. So this takes care of the starting point. This normalizes the chain code with reference to the starting point, but obviously it does not normalize the chain code with reference to the rotation. So to do that, okay, what we can do is simply we can take the number of direction, or rather we can check the first difference of the chain code. Okay, we can refer to the first difference of the chain code, meaning that how many direction changes are there if we are traveling in a particular direction. Let us say in the anti-clockwise direction. Okay, you see that how many chain code, how many direction changes are there. For example, let us choose, okay, a particular 4th direction code, okay, like this. Supposing this is the 4th direction code which we have chosen. Alright. Now, whenever we are going from 0 to 1, okay, how many direction changes are there in the anti-clockwise? 1, 2, 3 direction changes. Okay. So we call this code as 3, because while going from 0 to 1, okay, while going from 0 to 1, okay, in the anti-clockwise sense, you are traveling 1, 2, 3 clockwise direction, sorry. So while going in the clockwise direction from 0 to 1, we are having 1, 2, 3 direction changes. So we put 3 over here. When we go from 1 to 1, how many direction changes? 0. So when we are traveling from 1 to 1, it is 0. Whenever we are traveling from 1 to 0, how many direction changes? 1 direction change. Okay. Again 0 to 0 is 0 direction change. Again 0 to 0 is 0 direction change. 0 to 3 is 1 direction change. 3 to 3 is 1 direction change. 3 to 3 is 0 direction change. This one is 0. This one is 0. 3 to 2 is again 1 direction change. 2 to 2 is 0. 2 to 2 is 0. 2 to 2 is 0. 2 to 1 is 1 direction change. Okay. And then 1 to 1 is 0 direction change. Okay. And if you are trying to write it in the form of a circular code, okay, then you should also consider the direction change from this 1 to 0. And obviously 1 to 0, as we already said, 1 to 0 is 1 direction change. Okay. So this forms this is known as the first directional change. Okay. This is called as this we are referring to the first directional change of the chain code. Now if you make this code, okay, again if you normalize this code further, this first directional change code, if you normalize it further by giving shifts, you choose the starting point as the one that gives the minimum integer, then the chain code which you get, okay, what it is becoming? It is becoming invariant to rotation, it is becoming invariant to the starting point. Is that clear? This is the chain code that we get. Alright. Now, obviously this chain code is not the original chain code, but it is the first directional chain code. Okay. This is indicating that how many times the direction changes are taking place. So obviously if the object itself is rotated, okay, then the directional changes which we are going to get, okay, is going to be, the directional change will give rise to the same code. Obviously not this starting point, because the starting point might be different. So in order to make it invariant with respect to both rotation as well as the starting point, we should first take this first directional chain code, and thereafter we should choose the chain code which gives us the minimum integer. Okay, because the minimum integer is required for making it invariant to the starting point, and the first directional change gives us invariant with respect to rotation. Is this clear to you? Now obviously these normalizations are exact, okay, will give exact results, okay, provided the boundary itself is exact with reference to the rotation. Okay, many a times it so happens that when you have a boundary like this, okay, supposing this is the original boundary, and then you give a shift to this object, okay, and as a result of the shift, supposing this is the boundary which you get. And now this new boundary, in order to represent this new boundary, you consider the you have to resample the boundary once more, okay, in the new grid. Okay, you have rotated this image, so the resampled boundary points will become something like this. Now this resampled boundary points and the original boundary points, okay, may not be of very similar nature, okay, because of the resampling process, okay, because of the resampling process there will be some errors which will be introduced, okay, to the boundary pixels, okay, and if there are some errors in the representation of the boundary pixels themselves, okay, then even the chain code which you form will represent that change, isn't it? So obviously the method of chain code is exact only when your boundary representation, or only when your boundary is also going to be exact. Alright, so that is why this method doesn't become suitable when you have some noise along the boundary contour. Supposing instead of getting the object like this, you get the object something of this nature. Supposing this is the way you get the boundary. Okay. Now for this type of a representation, I mean, if you are choosing very fine grid spacing, supposing the grid spacing is much finer than the grid spacing which is indicated over here, okay, so as a result of this, what will happen? The number of chain code elements will increase, obviously, because there will be too many direction changes that take place, okay. The chain code length will be long, okay, and not only that, this all this noise along the boundary contour, okay, will indicate a change in the shape, okay, as compared to, I mean if you are comparing this shape, or rather the chain code of this particular object, okay, with the chain code of this one, the two chain codes are not going to match, okay. So remember that the representation based on chain code is highly sensitive to the noise present along the boundary, okay, boundary of the object, okay. And in order to reduce the effect of the noise, what people do many a times is to subsample the image into a coarser grid, okay. Supposing this same image, okay, having noisy boundary, if you are subsampling to a coarser grid, like say the grid which is indicated over here, okay, then the boundary pixels which you will get are these points itself, okay. So as a result of that, you will not observe the effect of noise. Okay, but if you are representing on a finer grid, okay, it will be more sensitive to noise. But obviously, if we are representing a boundary on a coarser grid, if we subsample and represent it on a coarser grid, what are we losing in the process? We are losing the accuracy of representation. Okay, but of course we are reducing the effect of noise on the boundary pixels. Is that clear to you? So now we will go over to yet another representation scheme which is very popularly known as the polygonal approximation. So the second representation scheme is a polygonal approximation. The idea is very simple. If you have a region, okay, whose boundary is, let's say typically a region is having a curved boundary, and supposing the boundary is of this nature. Okay. Now, in the method of polygonal approximation, essentially what we try to do is to segment these boundary pixels, okay, in such a manner that we have, okay, a minimum number of sides in a polygon, okay, and still we can accurately represent this particular boundary. Now, why I said minimum number of sides in a polygon? Because if I do not put any restriction on that, then you can obviously give me a solution. If there are n number of boundary points, okay, you can always give me a solution for a polygon having n number of sides. You can always say that I will take two points at a time, okay, and I will be joining those 2 points with a straight line, okay, and that will form an n-side polygon, okay. But we are not going into that, because although that representation, okay, will be the most accurate representation, but we are looking for a polygonal approximation so that a region or the boundary of a region can be described by minimum number of sides in a polygon. So what we are looking for is a solution of this nature. Okay, see, everywhere I have joined by straight line segments, okay, and I have formed a polygon, and basically this polygon which I have formed, okay, approximates the boundary, the actual boundary. The actual boundary is drawn with red color, drawn in red color, and the approximated boundary using straight line is drawn in the green color, okay, and you can clearly see that the green colored approximation is quite close to the red colored approximate boundary. But the question is that which method do we apply in order to get this kind of a polygon? Now for this, two different approaches are adopted. The first approach is what is called as merging. In the merging approach, what we do is we take any boundary pixel as a starting point. Let us say we consider this particular pixel as the starting point. Supposing this we take as the starting point, and from the boundary pixel and from that boundary pixel you keep on clubbing the other boundary pixels. Travel in one particular direction, let us say travel in the clockwise direction only, and you keep on merging boundary points to the starting boundary point. This is the starting boundary pixel, and to that you keep on clubbing other boundary pixels. Till what time? Till all these clubbed boundary points, they define a straight line segment that fulfills some least square measure. Okay, that is to say, we will try to fit straight lines. I mean, we will try to fit a single straight line with all these merged points. Okay, and we will be considering only those many boundary points. Okay, such that the least square error fit, okay, exceeds, I mean, till the time the least square error fit line exceeds a particular threshold. Okay, once the least square error fit exceeds a particular threshold, we stop clubbing further pixels. Like, say for example, by clubbing up to this point, maybe we will be finding that this does not satisfy the least square error fit anymore. Okay, so we will be considering only these boundary pixels as as a particular segment. Okay, and then we can join the two endpoints of the segment in order to approximate a straight line for the set of points which we have chosen. So once we stop over here, okay, we will once again start, okay, the merging process from this particular point. Okay, once we have started with this and come over here, okay, and saw that already this exceeds the preset threshold of the least square error fit, we stop and then we start from this point, and again we keep on accumulating edge points, okay, till the time we find that we cannot club any more pixels, okay, which can fulfill the least square error fit for the straight line segment. Okay, so in this manner we proceed, okay, till the time the entire contour is covered. Okay, and when we are changing whenever we are finding new straight line segments, okay, those points actually describe the vertices of the polygonal approximation. But do you realize a difficulty in this approach?
Just think of it.
Final point may coincide with the starting point. Final point may not coincide with the starting point.
Well, final point may not coincide with starting point. That is one aspect. Of course, there we can put some limit that whenever you encounter the starting point, you stop the line fitting there itself. Okay, possibly that condition we can bring about. Any other?
We have one extra edge possible if we start from middle of some segment, straight line segment.
Approximation of number of edges.
Well, what can happen in this case is that the vertices which we get, okay, may not correspond to the actual point of inflections present in the object boundary. Because after all, when are we stopping? We are stopping as soon as the least square error fit criteria is violated. Okay, as soon as the least square error is violated, we are stopping over there, and that need not correspond to the actual point of inflection along a curved contour. Okay, say for example, in this particular object, we are finding that this is a point of inflection. Okay, but it may be so possible that while trying to club all these points, okay, we may still find, I mean, supposing from this point we have started, and by clubbing the points along this contour, we still find that the least square error is not yet fulfilled. Okay, but somewhere over here we find that the least square error is already fulfilled, and we describe this segment like this. Okay, where this becomes a vertex. Okay, and obviously this vertex is not the correct vertex because it should have been a vertex point over here. Okay, that means to say where there is a genuine point of inflection present on the object boundary. So the difficulty with the merging approach is that the vertices may not correspond to the actual point of inflections along the boundary. There is yet another approach to polygonal approximation which is called as the splitting approach. In splitting approach, what we do is that we take, supposing this is the boundary of an object, okay, we take longer segments, okay, supposing we take a segment that joins from this point to this point, okay, or say for example not that long, supposing we take supposing we first divide this entire boundary, okay, into some arbitrary number of segments. Let us say that segments could be large segments, okay, so that our initial approximation to the polygon could be something like this. Now what we do, that when we consider a particular segment, okay, we also consider some measure of the deviation of this straight line from the actual boundary points. What we can do is, if we are considering, supposing this is the contour, okay, and we have chosen the line from here to here as the initial approximation of the segment, okay, we consider the boundary points and we draw perpendiculars, okay, from the boundary pixels to this approximated straight line, and we put some limit on the boundary. I mean we put some limit on the perpendicular distance, okay, that if the perpendicular distance exceeds a certain threshold, okay, then you split the segment there itself, okay, supposing this is the contour, okay, and this is your initial segment. So take every point along this contour, and supposing at this particular point we find that this has exceeded the perpendicular distance threshold, okay. So what we do now, we split the segment over here. Instead of taking this entire segment, we split the segment over here and consider this to be a two segment like this. Say this as one and this as yet another, okay. Instead of considering this entire segment, you consider this as one segment, this as one segment. Again, from this split segment, you try to find out that whether the perpendicular distance from the actual boundary point to this approximated straight line, that exceeds the threshold. If it exceeds the threshold, segment the boundary further. So what happens if this is the boundary, original boundary, and then you first find that this could be segmented into two portions like this, and afterwards you find that even this also can be segmented as follows. Supposing this also can be segmented. So like this we will be segmenting the contours further and further, okay, until some criteria for the perpendicular distance from the actual boundary point to the approximated straight line, okay, does not exceed a threshold, okay. And if we can satisfy this, okay, throughout the contour, then we can achieve a reasonable approximation to the polygon, a reasonable polygonal approximation, and this method is called as the splitting approach. Any question?
This method, will we have to change the limit of threshold every time?
Correct. This is a very interesting question. The question is that, do we have to keep a constant threshold or do we keep on changing the threshold? okay, it is a good approach to keep on changing the threshold, because we will be iteratively refining our approximation to the contour. Okay, so initially we had started with a long segment, and in that we will be keeping quite a large threshold value, so that somewhere over here the threshold is violated. Okay, now next time when we consider this segment and this segment, the threshold will be reduced. Okay, so one can adopt a variable threshold policy, or rather iteratively making the threshold lesser and lesser, so that the polygonal approximation is better. Any other questions?
How do we select the initial segmentation itself?
Well, selection of initial segment is quite arbitrary. Okay, like there is no harm if you choose very coarse length segments. Okay, that means to say, I mean, like at first what I considered was something like this. Okay, where I had I mean only a few, maybe 1, 2, 3, 4, 5, 6, 7 segments only we had considered. Okay, even if you consider with a single segment, okay, supposing if this is the contour and I start with a segment of this nature, okay, still I can keep on splitting and ultimately obtain a polygonal approximation. Okay, so only thing is that if I choose, if initially, I mean if I have some a priori knowledge about the object boundary, then possibly I can choose a much larger number of segments, I mean segments which will closely approximate the object boundary. If I do that, then I will need smaller number of iterations to find the exact contour. Any questions further? Now another approach towards the region representation is by the signatures, and I'll tell you what the signatures is. Normally the contour that you get, I mean the contour that you always get is a two-dimensional contour of an object, isn't it? Two-dimensional contour of a region. Now it is very often seen that if a two-dimensional signal can be converted to a one-dimensional signal, then the representation, or rather then then I mean computationally it looks much simpler. Okay, so this is what we are attempting to do. Supposing we have, I mean let us consider two different type of regions. One region is a circular region having a contour like this, and we have yet another region which is a square region like this. Now what we can do is we can take the, I mean we can consider the centroid of the region, and then from the centroid we consider the distance to the boundary point as we travel from the direction of 0 degree to 360 degree by moving in the anticlockwise direction. Okay, supposing this is the direction of 0 degree, this is the reference direction, okay, and this is the centroid of the circle. Supposing the circle is of radius r, let us say the circle is having a radius equal to r, and we consider small r as the distance from the centroid to the object boundary. Supposing this is the distance r, and the angle that it makes with respect to the reference axis is theta. Now if we plot, if we make a plot of theta in the x direction and r, that means to say the distance of the centroid to the boundary pixel, okay, if we keep that in the y-axis, then what type of curve are we going to get for the circle? We are going to get a straight line of amplitude what? Equal to capital R, because capital R is the radius of the circle. So we will be getting a signature of this nature, okay, where basically it is a plot of distance versus angle, okay. So it's a distance versus angle plot in which we get a straight line for a circle. This is the starting position, that is 0 degree, and this one is the angle 2 pi. Okay, so between 0 to 2 pi it is an absolute straight line if it is a perfect circle. If we have a square, supposing the centroid of the square is somewhere over here, okay. Now what type of distance versus angle curve are we going to get for this? Not exactly triangular. It will be something of this. Supposing the distance from here to here is A. We take this distance to be A. So the starting distance at 0 degree is equal to A. But when theta becomes equal to pi by 4, okay, supposing this is the position for pi by 4, at pi by 4 we will get distance equal to root 2a. Okay, again when we are going over to pi by 2, we will be having a distance equal to a again, okay, again pi by again root 2a after further pi by 4 travel like this, and the curve, nature of the curve will be something of this nature. So like this you will be getting how many peaks within the limits of 0 to 2 pi? You will be getting 4 peaks, because one peak will be when the angle is this much, another peak is when the angle is this, another peak is corresponding to this, and another peak is corresponding to this. So corresponding to 4 corners we will be getting 4 peaks over here. Now again this kind of a signature, okay, is it invariant with respect to translation, rotation and scaling? Obviously it is invariant with respect to translation, because even if we translate this square to somewhere else, okay, still since it is with respect to the centroid, the nature of this curve is not going to change. But obviously it is not going to be invariant with respect to, no, it is also going to be invariant with respect to rotation, because even if we rotate this particular object, okay, this is going to be this nature of the curve is going to be obviously invariant, but only thing is that it will not be invariant with respect to the starting position. It is not invariant with respect to starting position, and for that can you think of some method whereby we can make it starting position invariant? It is very simple. You define the starting position, okay, you choose a particular starting position, and supposing you choose the starting position in such a manner that the distance from the centroid to the object boundary is maximum, okay, choose that point as the starting one, okay, where the distance from the centroid to the object boundary is maximum. In this case, of course, any of these 4 points could have been the starting point, okay, but typically an object may not be like this. For example, supposing this is the centroid of an object, and you are getting the object like this, and supposing this is the farthest point, okay, in that case you choose this as the starting point, okay, and is it invariant with respect to scaling of the object? Yes, amplitude is going to change. If I make, if instead of considering a square of this, supposing I make a smaller square, okay, the nature will not change obviously, but obviously the amplitude will change. So possibly we will get the new curve like this. So in order to make this signature invariant with respect to size, what one can do is a further normalization. Means instead of representing the signature within amplitude 0 to root 2a, okay, you represent it with respect to the amplitude ranging in the, having the range of 0 to 1. Always if you are normalizing the amplitude within limit 0 to 1, okay, then you can make the signature invariant with respect to size. Okay, so many, quite often these kind of one-dimensional signatures are used for representing the boundary of a region. Okay, of course, even this method is not quite suitable when we have a very noisy boundary, because if we have a noisy boundary, okay, in that case we will be having too many local maximas present in the signature. Okay, and it is very difficult to do matching of one signature with a reference signature when we have a noisy boundary. But for a clean boundary, okay, noiseless, noise-free boundary, this kind of one-dimensional signatures, okay, seem to be quite useful. Any questions? Thank you.